There's a gap in Earth's history that spans roughly 20 million years, not a gap in our knowledge, a gap in the actual rock record itself. A period where layers of stone that should exist simply don't, where geological time seems to have been erased from the planet's memory, leaving behind one of the most puzzling mysteries in all of Earth science. If you're using this to fall asleep, that's literally why I make them. So subscribe maybe and tell me where you are and what time. I check comments and it's like Melbourne at midnight, Minneapolis at morning, all at once. This isn't like other geological mysteries where we're missing fossils or can't interpret ancient climates. This is different. This is about missing time itself. Enormous chunks of Earth's chronological record that vanished so completely that for over a century, geologists thought they were looking at continuous rock formations when they were actually staring at gaps that represented millions upon millions of missing years. The discovery began with a Scottish farmer named James Hutton in the late 1700s, but it wasn't until the 1960s that scientists realized the true scope of what they were dealing with. What they found challenged everything we thought we knew about how geological time works, how rock layers form, and how the Earth records its own history. They found evidence of something that shouldn't be possible, entire eras of geological time that had been cleanly excised from the rock record, as if someone had taken scissors to the planet's timeline and cut out decades of millions of years at a time. The phenomenon is called an unconformity, but that clinical term doesn't capture the profound weirdness of what's actually happening. When you stand at certain locations around the world and look at rock faces, you're seeing layers that were deposited hundreds of millions of years apart, sitting directly on top of each other, with no transition, no gradual change, nothing to indicate that enormous spans of time passed between their formation. It's like opening a book and finding that page 100 is followed immediately by page 20,000, with no acknowledgement that 19,900 pages are missing. Except in this case, each missing page represents thousands of years of Earth's history. The most famous example is the Great Unconformity, a gap in the geological record that exists on every continent on Earth. In some places, it represents a missing span of over 1 billion years. Billion, with a B. That's not a typo. At the Grand Canyon, you can literally put your hand on rock layers that are separated by 1.2 billion years of missing time. Your fingers span more than 1 billion years of Earth's history that simply isn't there anymore. But here's the thing that makes it truly mysterious. We have no idea where that time went. The rocks that should represent those missing years didn't just disappear. They were never preserved in the first place, or they were preserved and then removed so completely that no trace of them remains. Not even fragments, not even chemical signatures, nothing. This is fundamentally different from other types of erosion or geological recycling. When normal erosion removes rock layers, it leaves evidence. You can see where material was transported, where it was deposited, how the landscape changed over time. But the Great Unconformity shows no such evidence. The missing rock layers vanished as if they never existed, leaving behind contacts between remaining layers that are so clean, so precise that they look artificial. When geologists first started mapping these unconformities in detail, they made a discovery that deepened the mystery even further. The gaps weren't random. They weren't scattered across different time periods or different locations according to local geological conditions. Instead, they clustered around specific time periods, as if something was systematically removing parts of Earth's geological record at regular intervals. The Great Unconformity, the most extensive of these gaps, occurs at almost exactly the same time period across the entire planet. From North America to Australia to Antarctica, rock layers dating to between 1.2 billion and 550 million years ago are simply missing. This suggests that whatever caused the Great Unconformity wasn't a local phenomenon. It was global, synchronized, and powerful enough to erase geological evidence across entire continents simultaneously. But what force could possibly operate on that scale? The leading hypothesis involves something called snowball Earth, periods when the entire planet was covered in ice from pole to pole, with glaciers potentially miles thick grinding across every land surface on the planet. During snowball Earth events, these massive ice sheets would have acted like planetary-scale sandpaper, scraping away exposed rock formations and transporting the debris to places where it could be completely recycled back into the Earth's interior. But even this explanation has problems. Glacial erosion, no matter how extensive, should leave evidence. There should be characteristic patterns in the remaining rock, distinctive minerals transported from their original locations, chemical signatures that indicate glacial activity. In many places affected by the Great Unconformity, these signatures are absent or inconsistent with pure glacial erosion. Some researchers have proposed that the missing time was removed by something even more dramatic. Massive episodes of crustal recycling where entire sections of the Earth's surface were somehow drawn back into the planet's interior and completely reprocessed. This would explain the complete absence of evidence for the missing time periods. If the rocks were actually consumed by geological processes rather than just eroded away, they wouldn't leave traces in the remaining geological record. But this explanation raises its own questions. What could drive such massive crustal recycling? And why would it happen synchronously across the entire planet? The mystery deepens when you look at what happened immediately after these unconformities. The rock layers that were deposited after the Great Unconformity show signs of rapid, dramatic changes in Earth's environment. The Cambrian explosion, the sudden appearance of complex life forms in the fossil record, happens almost immediately after the Great Unconformity ends. It's as if the erasure of those billion years of geological time somehow reset the planet's biological systems and allowed evolution to suddenly accelerate. This timing can't be coincidental. Something about the processes that created the Great Unconformity also created conditions that enabled the most significant evolutionary event in Earth's history. But what's really strange is that we can see similar patterns at smaller scales throughout the geological record. There are dozens of smaller unconformities scattered through Earth's timeline, each representing missing chunks of time ranging from thousands to millions of years. And many of these smaller gaps are also followed by periods of rapid environmental change or evolutionary innovation. It's as if the Earth periodically erases parts of its own history, and these erasure events somehow catalyze new chapters in the planet's development. Some researchers have suggested that unconformities aren't just gaps in the rock record, they're windows into processes that operate on timescales so vast that we can barely comprehend them. Maybe the Earth has natural cycles of geological recycling that happen every few 100 million years. Cycles so fundamental to how the planet works that they shape everything from the evolution of life to the formation of continents. But these cycles would be essentially invisible from a human perspective. They operate on timescales millions of times longer than human civilization has existed. To understand them, we have to piece together evidence from rock formations that span billions of years, looking for patterns that emerge only when you zoom out to a planetary perspective. The challenge is that each unconformity erases the evidence we need to understand the processes that created it. We're trying to solve a mystery where the main evidence has been systematically destroyed by the phenomenon we're investigating. It's like trying to understand a crime where the criminal has erased all traces of their actions, except in this case, the crime might be a natural process that's been operating since the Earth formed. But there are clues. The boundaries between rock layers on either side of unconformities often show distinctive chemical and mineral signatures that provide hints about what conditions were like during the missing time periods. Some of these signatures suggest extreme environmental conditions, temperatures, pressures, or chemical compositions that would have been incompatible with preserving normal rock layers. Other signatures suggest rapid changes in sea level, atmospheric composition, or even the planet's magnetic field strength. Taken together, these clues paint a picture of a planet that periodically undergoes fundamental transformations so complete that they reset the geological record. But let's get more specific about what it actually means to have 1 billion years of time missing from the rock record. Because when we say missing time, we're not talking about gaps in our knowledge or places where fossils are rare. We're talking about something far more profound and disturbing. Picture yourself as a geologist in the early 1900s, before we had sophisticated dating techniques, before we understood plate tectonics, before we knew how old the Earth really was. You're studying rock formations, trying to piece together the story of the planet's past by reading the layers like pages in a book. And you come to a place where ancient crystalline rocks, the kind formed deep underground under intense heat and pressure, are sitting directly underneath much younger sedimentary rocks filled with fossils of complex life forms. There's no gradual transition, no evidence of the processes that should have brought the deep rocks to the surface. No indication of how much time passed between the formation of the lower rocks and the deposition of the upper layers. It's like finding a medieval manuscript page glued directly to a computer printout with no explanation of how they came to be together or what happened to all the centuries of writing that should exist between them. This is what geologists found at location after location around the world. The same pattern, the same mysterious contact between very old rocks and much younger rocks, with vast periods of time apparently missing in between. They called it an unconformity, but that term barely captures the strangeness of what they were observing. At Sycamore Point in Scotland, where James Hutton first recognised unconformities in the 1780s, you can see vertical layers of ancient rock that have been worn flat and then covered by horizontal layers of much younger rock. The vertical layers represent millions of years of sediment deposition, followed by millions of years of mountain building that tilted the layers vertical, followed by millions of years of erosion that wore the mountains down to a flat surface. And then, sitting on top of that flat surface as if nothing unusual had happened, are more millions of years of horizontal sediment layers representing a completely different geological era. The time represented by all that mountain building and erosion, the entire cycle of uplift and destruction that created the flat surface, is simply absent from the record. Not recorded anywhere, not preserved in any form. It's as if the Earth took a multi-million-year break from keeping track of its own history. But Sycamore Point is nothing compared to the scale of the great unconformity. At the Grand Canyon, the contact between the ancient basement rocks and the overlying sedimentary layers represents a gap of over 1.2 billion years. 1.2 billion years. That's more time than has elapsed since complex life first appeared on Earth. More time than the entire Phanerozoic eon, the geological era that includes all of Earth's history with abundant life. During that missing 1.2 billion years, entire mountain ranges rose and were completely eroded away. Oceans opened and closed. The first complex cells evolved. The atmosphere's oxygen content rose to levels that would support animal life. The first simple multicellular organisms appeared. All of that happened during the missing time represented by the great unconformity, and none of it left any geological trace in the places where the unconformity exists. It's not just that the fossils are missing or that the sedimentary layers are thin. The rocks that would record those events are completely absent, as if they were never there at all. This creates a paradox that geologists are still struggling to resolve. We know those billion years of Earth history happened because we can see evidence for them in other locations around the world. but in the places affected by the Great Unconformity, it's as if time jumped forward from 1.7 billion years ago to 500 million years ago without any intervening period. The precision of this time gap is what makes it so mysterious. If the missing rocks had been removed by normal erosion processes, we would expect to see variation in how much material was removed from different locations. Some places would be missing more time, others would be missing less, depending on local conditions. Instead, the Great Unconformity shows remarkably consistent time gaps across vast distances. From Arizona to Montana to the Canadian Shield, the same billion years are missing with startling precision. This suggests that whatever process created the Great Unconformity operated simultaneously across the entire North American continent and beyond. Similar unconformities from the same time period exist on every continent on Earth. The scale and synchronization required for such an event challenges our understanding of how geological processes work. Normal geological processes, erosion, sedimentation, volcanism, even plate tectonics, operate on regional scales with lots of local variation. Mountain ranges rise in some places while valleys form in others. Rivers erode their banks while deltas build up at their mouths. Volcanoes destroy landscapes in some regions while others remain stable for millions of years. But the Great Unconformity affected the entire planet simultaneously, removing the same time periods from the geological record with clockwork precision. This points to a global-scale process that we don't fully understand, something that could coordinate geological activity across thousands of miles and multiple continents. The most widely accepted explanation involves the snowball Earth hypothesis. The idea that the planet was completely frozen for extended periods during the time represented by the Great Unconformity. During snowball Earth events, ice sheets potentially several miles thick would have covered the entire planet's surface, from the poles to the equator. These ice sheets would have been grinding against the underlying rock constantly, scraping away surface layers and transporting the debris to locations where it could be completely subducted back into the Earth's interior. The scale of erosion during a snowball Earth event would have been unlike anything in more recent geological history. Modern glaciers can carve out valleys and reshape landscapes over thousands of years, but snowball Earth glaciers would have been operating for millions of years with the power of an entire planet's ice volume behind them. They could have literally ground down entire mountain ranges to sea level, removing not just surface rocks, but the deep, crustal roots that normally preserve evidence of ancient mountain-building events. And when the ice finally melted, the rebound of the Earth's crust from the removal of all that ice weight would have created additional geological instability, potentially triggering massive volcanic events that could have further obscured or destroyed remaining evidence from the pre-glacial period. But even the snowball Earth hypothesis has problems explaining all the features of the Great Unconformity. For one thing, we should see much more evidence of glacial activity if ice sheets were responsible for removing billions of years' worth of rock layers. Glaciers leave distinctive signatures in the geological record. Characteristic patterns of erosion, distinctive sediment types, chemical markers that indicate ice-dominated environments. In many locations affected by the Great Unconformity, these glacial signatures are weak or absent entirely. The contact between the older and younger rocks is too clean, too precisely defined to be the result of glacial grinding. Some locations show what appears to be chemical weathering rather than physical erosion, as if the missing rocks were dissolved away rather than scraped away. But the scale of chemical weathering required to remove billion-year spans of geological history would have required environmental conditions unlike anything we see on Earth today. Other locations show evidence of what geologists call beveling, the systematic removal of rock layers at precise angles, creating geometric patterns that look almost artificial. natural erosion processes rarely create such regular geometric removal patterns. These features have led some researchers to propose even more exotic explanations for the great unconformity. One hypothesis suggests that the missing time periods coincide with periods of intense bombardment by asteroids or comets, impact events so severe that they literally vaporized surface rocks across entire continents. The late heavy bombardment, which occurred around 4 billion years ago, provides a precedent for solar system-wide bombardment events. But the Great Unconformity is much more recent, and there's little evidence for the kind of massive impact events that would be required to remove billion-year spans of geological history. Another hypothesis involves dramatic changes in sea level that could have exposed vast areas of the ocean floor to erosion processes that don't operate under normal conditions. If global sea levels dropped by thousands of feet, far more than any sea level change we've observed in recent geological history, enormous areas of normally submerged ocean floor would have been exposed to atmospheric weathering. The chemical processes that normally preserve sediments underwater would have stopped operating, and new erosion processes would have begun breaking down rocks that had been stable for millions of years. But this explanation also requires environmental changes far more extreme than anything we can document from other periods of Earth's history. A third hypothesis suggests that the Great Unconformity might be related to fundamental changes in the Earth's internal structure, rearrangements of the planet's core and mantle that affected surface geology in ways we don't fully understand. The Earth's core and mantle are constantly in motion, with currents and convection patterns that influence everything from magnetic field strength to volcanic activity to the movement of continents. Major reorganizations of these deep Earth systems could potentially create surface effects dramatic enough to erase geological evidence across entire continents. Some geophysicists think that the Earth's core might undergo periodic flips or reorganizations that completely change the planet's magnetic field structure and internal heat distribution. During such events, the normal processes that preserve geological evidence might be completely disrupted. Surface rocks might be subjected to heat, pressure, or chemical conditions that would cause them to metamorphose or melt entirely, removing their original characteristics and the time information they contained. But like the other explanations, this core reorganization hypothesis is highly speculative and difficult to test with current technology. The truth is that we don't have a fully satisfactory explanation for the Great Unconformity or for the many smaller unconformities scattered throughout the geological record. What we do have is clear evidence that the Earth periodically undergoes processes that completely erase parts of its own geological memory. These processes operate on scales, both spatial and temporal, that dwarf human experience. They involve forces powerful enough to remove evidence of entire geological eras, synchronized enough to operate simultaneously across multiple continents, and systematic enough to target specific time periods with remarkable precision. Understanding these processes is crucial for understanding how the Earth really works over deep time, but they're almost impossible to study directly because their main effect is to destroy the evidence we would need to understand them. It's like trying to study a shredding machine by examining the confetti it produces. The process of destruction removes the information we need to understand the destruction process itself, but there are indirect ways to study unconformities and the processes that create them. One approach involves looking at locations where unconformities exist but are less complete, places where some evidence from the missing time periods has survived. These partial unconformities can provide clues about what conditions were like during the erasure events and what processes were responsible for removing most of the evidence. Another approach involves studying the rocks that exist immediately before and after unconformities to look for chemical or mineralogical signatures that might indicate what happened during the missing time periods. Even if the rocks from the missing periods are gone, they might have left traces in the rocks that survived, changes in mineral composition, isotopic ratios, or trace element concentrations that reflect the environmental conditions during the erasure events. A third approach involves looking for evidence of unconformity-creating processes in other parts of the solar system. If the forces that create unconformities on Earth are related to solar system-wide processes, changes in solar radiation, gravitational influences from other planets, impacts from asteroids or comets, then we might see similar features on other planets or moons. Mars, in particular, shows evidence of geological processes that might be related to the forces that create unconformities on Earth. The Martian surface shows massive erosion features that appear to have been created very rapidly by processes that no longer operate on the planet. Entire regions of Mars show evidence of surface layers that were stripped away completely, leaving behind contacts between very old and much younger surface features. Some of these Martian unconformities appear to have been created at the same time periods as major unconformities on Earth, suggesting that they might be related to solar system-wide processes rather than processes specific to either planet. The moons of the outer planets also show evidence of surface features that might be related to unconformity-creating processes. Europa, one of Jupiter's moons, has a surface that appears to be completely renewed every few million years through processes that erase all evidence of previous surface features. Enceladus, one of Saturn's moons, shows evidence of episodic resurfacing events that completely remove older surface features and replace them with new ones. If these processes are related to the forces that create unconformities on Earth, they might provide clues about the mechanisms involved and the timescales on which they operate. But studying unconformities on other worlds is challenging because we have limited access to their geological records and no way to directly sample their surface materials. Most of our understanding of extraterrestrial geology comes from orbital observations and remote sensing data, which can reveal surface features but can't provide the detailed chemical and mineralogical information needed to understand the processes that created those features. Still, the fact that unconformity-like features appear to exist throughout the solar system suggests that the processes responsible for the great unconformity on Earth might be fundamental aspects of planetary evolution rather than unique events specific to our planet. This has implications for understanding the history of life on Earth and the potential for life on other worlds. If unconformity-creating processes are common features of planetary evolution, then the geological records of all planets might be full of missing time periods that contain crucial information about planetary development. On Earth, many of the major transitions in the history of life, the evolution of complex cells, the development of multicellular organisms, the emergence of sexual reproduction, the evolution of photosynthesis, occurred during time periods that are partially or completely missing from the geological record due to unconformities. Our understanding of how these biological innovations developed is necessarily incomplete because the geological evidence for the environments in which they evolved has been erased. If life exists on other planets, it might have undergone similar evolutionary transitions during time periods that are now missing from their geological records due to their own versions of the Great Unconformity. This could make it extremely difficult to understand the history of life on other worlds, even if we eventually develop the technology to study their geological records in detail. But unconformities might also provide opportunities for understanding planetary processes that would otherwise be invisible. The fact that unconformity creating processes can erase billions of years of geological evidence means that they represent some of the most powerful forces operating on planetary scales. Understanding these forces could provide insights into fundamental aspects of planetary physics and chemistry that we can't study any other way. For example, unconformities might be windows into understanding how planetary cores and mantles evolve over billions of years. The internal structure of planets is constantly changing as they cool and differentiate, but these changes happen so slowly that we can't observe them directly. But if unconformities are created by periodic reorganizations of planetary interiors, then studying the timing and global distribution of unconformities might allow us to reconstruct the history of planetary internal structure in ways that would otherwise be impossible. Similarly, unconformities might provide insights into how planetary atmospheres and hydrospheres evolve over geological time. The extreme environmental conditions required to create unconformities probably involve dramatic changes in atmospheric composition, ocean chemistry, and climate patterns. By studying the traces of these conditions preserved in the rocks that survived unconformity events, we might be able to reconstruct ancient environmental conditions that were far more extreme than anything we see today. This could help us understand the full range of environmental conditions that planets can experience and the processes that drive transitions between different environmental states. Such understanding could be crucial for predicting how Earth's environment might change in the future, especially as human activities begin to alter global environmental conditions at rates that approach those associated with major geological transitions. Are we inadvertently triggering processes that could lead to future unconformities? Could human-induced changes in atmospheric composition, ocean chemistry, or global temperature push Earth's environmental systems beyond thresholds that lead to geological record erasure? We don't know because we don't understand the environmental thresholds that trigger unconformity-creating processes. But the existence of the Great Unconformity and other major unconformities suggests that Earth's environmental systems can undergo transitions so dramatic that they reset the geological record. If human activities are pushing Earth's systems towards similar transitions, the consequences could be far more severe than current climate models predict. Climate change research focuses primarily on changes that occur over decades to centuries, the timescales relevant to human civilization and current ecosystems. But unconformities represent changes that occur over millions of years and can erase evidence of entire geological eras. If current environmental changes are part of a longer-term transition toward unconformity-creating conditions, we might be in the early stages of environmental changes that will ultimately be far more dramatic than anything we're currently preparing for. The missing time periods represented by unconformities might provide glimpses of Earth's environmental future, periods when normal geological processes are completely disrupted and the planet's surface undergoes fundamental reorganization, but they might also represent opportunities for dramatic innovation and change. Many of the most significant biological and geological innovations in Earth's history occurred immediately after major unconformities. The Cambrian explosion, the rapid diversification of complex life forms that marked the beginning of the modern biological world, occurred immediately after the end of the time period represented by the Great Unconformity. This timing is probably not coincidental. The extreme environmental conditions that created the Great Unconformity might also have created opportunities for evolutionary innovation that wouldn't have been possible under normal conditions. If unconformities represent periods of environmental reset, then they might also represent periods when the normal constraints on biological and geological processes are temporarily suspended. During such periods, evolution might be able to explore possibilities that are normally blocked by existing ecosystems and environmental conditions. Similarly, geological processes might be able to create new types of rock formations, mineral deposits, and surface features that wouldn't form under normal conditions. The world that emerges after an unconformity event might be fundamentally different from the world that existed before, not just because of the missing time, but because of the new possibilities that the unconformity process makes available. From this perspective, unconformities aren't just destructive events that erase parts of Earth's history. They might be creative events that enable new chapters in planetary evolution. But this creative aspect of unconformities is almost impossible to study directly because, by definition, the most dramatic changes occur during the missing time periods that the unconformities represent. We can see the before and after states, but we can't observe the transition itself. It's like studying the results of a chemical reaction without being able to observe the reaction process. We can analyze the starting materials and the final products, but the mechanism that transforms one into the other remains largely mysterious. This is one of the most frustrating aspects of studying unconformities. The processes we most want to understand are precisely the processes that are least accessible to direct observation. But it's also what makes unconformities so fascinating from a scientific perspective. They represent natural experiments in planetary evolution conducted on scales and timescales that we could never replicate artificially. Each unconformity is a record of what happens when Earth's systems are pushed beyond their normal operating limits and into regimes where entirely different processes take over. By studying the patterns of unconformities across Earth's history, we might be able to understand the fundamental limits of planetary environmental stability and the processes that drive transitions between different types of planetary states. This understanding could be crucial for assessing the long-term habitability of Earth and other planets. If planets naturally undergo periodic unconformity events that dramatically alter their surface environments, then long-term habitability might depend not just on maintaining stable conditions, but on surviving and adapting to periodic episodes of extreme environmental change. Life on Earth has clearly survived multiple unconformity events, but we don't understand how it managed to do so or what characteristics enabled it to persist through environmental changes dramatic enough to erase most of the geological record. Understanding these survival mechanisms could be crucial for ensuring the long-term survival of life on Earth, especially as human activities begin to alter global environmental conditions in ways that might trigger future unconformity events. But survival might not be the only consideration. If unconformities represent periods of enhanced innovation and change, then they might also represent opportunities for life to undergo evolutionary transitions that wouldn't be possible under stable conditions. The history of life on Earth shows repeated episodes of dramatic innovation and diversification that occur immediately after major environmental transitions. These innovations don't just help life survive environmental change. They often lead to entirely new forms of biological organization and complexity that become the foundation for subsequent evolutionary development. From this perspective, unconformities might not just be obstacles to be survived, but opportunities to be exploited. If we can understand the mechanisms that drive innovation during unconformity events, we might be able to harness those mechanisms to accelerate beneficial evolutionary and technological changes. This could be particularly relevant for addressing long-term challenges like space colonization, where human survival might depend on adapting to environmental conditions that are completely different from those on Earth. The extreme environmental conditions associated with unconformity events might provide natural laboratories for understanding how life can adapt to conditions that don't exist on Earth today. By studying the innovations that occurred during past unconformity events, we might gain insights into the types of adaptations that could enable life to survive and thrive in the extreme environments found on other planets. But this research is still in its early stages. We're only beginning to understand the basic patterns of unconformities in Earth's geological record, and we know almost nothing about the detailed processes that create them or the biological and geological innovations they enable. Future research on unconformities will probably require new technologies and approaches that don't exist yet. We need better techniques for detecting and dating unconformities, especially smaller ones that might be difficult to identify with current methods. We need better ways of reconstructing environmental conditions during unconformity events using chemical and isotopic signatures from rocks that survived the erasure processes. We need better theoretical frameworks for understanding how planetary systems can undergo transitions dramatic enough to erase their own geological records, and we need better ways of integrating information from different planets and moons to understand whether unconformity-like processes are universal features of planetary evolution or unique characteristics of Earth. But even with current limitations, unconformities provide a unique window into aspects of planetary evolution that we couldn't study any other way. They remind us that planets are dynamic systems that can undergo changes far more dramatic than anything we observe over human timescales. They suggest that the stable environmental conditions that have characterized human history might be temporary intervals between much more dramatic episodes of planetary change. And they provide evidence that some of the most important transitions in Earth's history might have occurred during time periods that are now completely missing from the geological record. Yet there's something even more unsettling about unconformities when you really think about what they mean for our understanding of reality itself. Every scientific field relies on the assumption that evidence accumulates over time, that the past leaves traces in the present that we can study and interpret, that natural processes create records of their activity that persist long enough for us to discover and analyze them. But unconformities violate this fundamental assumption. They represent processes that systematically destroy their own evidence, that operate specifically to erase the traces of their activity from the geological record. It's as if the Earth has a built-in mechanism for forgetting its own past, for ensuring that certain chapters of its history remain permanently inaccessible to future investigation. This raises profound questions about the nature of knowledge and the limits of scientific inquiry. If some natural processes are specifically designed to erase evidence of their activity, then there might be entire categories of phenomena that are inherently unknowable. We might be living in a universe where some of the most important processes operate in ways that make them invisible to scientific investigation, not because they're too small or too fast or too far away, but because they systematically destroy the evidence that would allow us to study them. This possibility is deeply disturbing to the scientific worldview, which is based on the assumption that persistent observation and careful analysis can eventually reveal the mechanisms underlying any natural phenomenon. But unconformities suggest that this assumption might be wrong. Some phenomena might be inherently self-erasing, operating in ways that ensure they remain mysterious no matter how sophisticated our investigative techniques become. The great unconformity might be just the tip of the iceberg. There might be other categories of self-erasing phenomena that we haven't discovered yet, processes that operate on even larger scales or longer timescales and remove even more evidence of their activity. Our entire understanding of the universe might be based on the small fraction of natural processes that happen to leave permanent traces, while the majority of cosmic activity might be inherently unknowable because it systematically erases its own evidence. This would mean that science, rather than gradually approaching a complete understanding of reality, might actually be exploring an ever-shrinking island of knowable phenomena surrounded by vast oceans of inherently mysterious processes. Every scientific discovery might reveal new categories of unknowability, new types of phenomena that operate in ways that make them permanently inaccessible to investigation. From this perspective, the prehistoric time holes represented by unconformities aren't just geological curiosities. They're warnings about the fundamental limits of human knowledge and the possibility that reality itself might be structured in ways that ensure certain truths remain forever hidden. But there's another possibility, one that's even stranger and more difficult to contemplate. Maybe the missing time periods represented by unconformities don't exist in the past at all. Maybe they exist in some other dimension of reality that we don't have access to, but that occasionally intersects with our normal space-time in ways that leave traces in the geological record. This interpretation draws on speculative physics, suggesting that time might have multiple dimensions or that our universe might be embedded in higher dimensional spaces with different temporal structures. If this is true, then the missing billion years of the Great Unconformity might not be missing at all. They might exist in a parallel temporal dimension that normally doesn't interact with our own, but that occasionally comes into contact with our reality at specific geological locations. The unconformity boundaries might be interfaces between different temporal dimensions, places where time streams with different properties meet and create discontinuities in the normal flow of geological time. This would explain why unconformities appear so suddenly and precisely in the geological record. They're not the result of gradual erosion or environmental change, but of discrete intersections between different temporal realities. It would also explain why unconformity-creating processes seem to operate according to rules that are different from normal geological processes. They're not geological processes at all, but manifestations of higher dimensional physics that we don't yet understand. This interpretation is highly speculative and not accepted by mainstream geology or physics, but it's worth considering because it provides a framework for thinking about unconformities that doesn't require them to violate the normal rules of geological processes. If unconformities are interfaces between different temporal dimensions, then their strange properties, their precision, their global synchronization, their ability to erase evidence completely become features rather than bugs. They're not violations of normal geological processes, but examples of higher-order processes that operate according to different rules entirely. This perspective also suggests that unconformities might be windows into aspects of reality that are normally hidden from us. By studying the boundaries between different temporal dimensions, we might gain insights into the structure of time itself and the ways that different types of temporal flow can interact and influence each other. This could have implications far beyond geology. If time has multiple dimensions and different types of temporal flow, then our understanding of causality, determinism, and the relationship between past, present, and future might need to be fundamentally revised. The missing time periods represented by unconformities might not be lost forever. They might still exist in parallel temporal dimensions that we could potentially access if we developed the right theoretical frameworks and investigative techniques. But even if we reject these exotic interpretations, unconformities still represent something profound about the nature of time and the mechanisms that govern the preservation of information about the past. They remind us that time is not simply a neutral medium in which events occur and are recorded. Time itself might be an active agent that participates in determining which events leave permanent traces and which events disappear without a trace. The flow of time might not be uniform or consistent. There might be periods when time operates according to different rules, when the normal mechanisms of information preservation are suspended or altered in ways that create gaps in the historical record. This possibility challenges our most basic assumptions about the nature of reality and the reliability of our methods for understanding the past. If time itself can be discontinuous, if the mechanisms that preserve information about past events can be periodically suspended, then the entire enterprise of historical science becomes much more uncertain and contingent than we typically assume. We might be living in a universe where the past is not fixed and permanent, but fluid and subject to revision by processes that operate on timescales we can barely comprehend. The missing time periods represented by unconformities might not be static gaps but active zones of temporal uncertainty where the normal rules of causality and information preservation don't apply. This would mean that our understanding of Earth's history is not just incomplete but potentially unstable. New unconformity events could theoretically alter or erase parts of the geological record that we currently consider well established, changing our understanding of past events in ways that we can't predict or control. But perhaps the most unsettling implication of unconformities is what they suggest about our own place in the flow of geological time. We tend to think of human history as permanent, as something that will leave lasting traces in the geological record for millions of years to come. The Industrial Revolution, the development of nuclear weapons, the widespread use of plastics, the dramatic alterations to global climate patterns. All of these seem like such dramatic changes to Earth's environment that they should be preserved in the rock record for geological ages. But unconformities suggest that even the most dramatic environmental changes can be completely erased from the geological record if the right conditions occur. The billion years of missing time represented by the Great Unconformity included periods of dramatic environmental change, the evolution of complex life forms, major alterations to atmospheric composition, and massive geological events that would seem to be permanent and unmistakable. Yet all of that was erased so completely that we can barely detect its absence, let alone reconstruct what actually happened during those missing periods. If the Earth can erase 1 billion years of its own history without leaving a trace, it can certainly erase the few thousand years of human influence on the planet. Our entire civilization, from the first agricultural settlements to the most advanced space technology, might someday become part of a missing time period, an unconformity that removes any evidence that human beings ever existed on Earth. Future geologists studying the planet millions of years from now might find clear evidence for the age of dinosaurs and clear evidence for whatever form of life evolves after humanity, but no trace whatsoever of the brief period when humans dominated the planet's surface. This possibility forces us to confront the fundamental impermanence of everything we consider important and lasting. The cities we build, the monuments we erect, the technologies we develop, the changes we make to the environment, all of it might be just temporary fluctuations in Earth's surface conditions, destined to be erased by the next major unconformity event. But there's another way to think about unconformities that's perhaps more hopeful and less existentially disturbing. Instead of seeing them as destructive forces that erase parts of Earth's history, we might think of them as creative forces that enable new possibilities for planetary development. The Cambrian explosion, which produced most of the major groups of complex animals that exist today, occurred immediately after the end of the Great Unconformity. This timing suggests that the processes that create unconformities might also create opportunities for dramatic innovation and change that wouldn't be possible under normal geological conditions. The extreme environmental conditions associated with unconformity events might act as powerful selection pressures that drive rapid evolutionary innovation. During these periods, the normal constraints on biological and geological processes might be temporarily suspended, allowing new forms of organization and complexity to emerge that would be impossible under stable conditions. From this perspective, unconformities aren't just episodes of destruction, but episodes of creative destruction that clear away existing structures and enable the emergence of new and more complex forms of organization. The missing time periods they represent might be periods of intense creativity and innovation when the most important developments in Earth's history occurred. If this interpretation is correct, then unconformities might be essential features of planetary evolution rather than unfortunate accidents that destroy valuable historical information. They might be the mechanisms through which planets undergo fundamental transitions from one type of organization to another, the processes that enable the emergence of new levels of complexity and sophistication in planetary systems. But this creative aspect of unconformities is almost impossible to study directly because the evidence for the creative processes is erased along with everything else during unconformity events. We can see the results, the new forms of life and geological organization that appear after unconformities, but we can't observe the processes that created them. This creates a fundamental limitation in our ability to understand how innovation and creativity operate on planetary scales. The most important episodes of creativity in Earth's history might be precisely the episodes that are least accessible to scientific investigation. But maybe that's the point. Maybe the processes that drive major innovations in planetary evolution require conditions that are incompatible with normal information preservation. Maybe creativity on geological scales requires the destruction of existing information structures, the erasure of past constraints, the opening of possibilities that can only emerge when the past is forgotten rather than remembered. From this perspective, the self-erasing nature of unconformity processes isn't a bug, but a feature. It's not an unfortunate side effect of powerful geological processes, but an essential component of how those processes enable planetary innovation. The prehistoric time holes that no one can explain might be necessary components of a creative process that operates on scales too large and timescales too long for us to comprehend directly. They might be the empty spaces that must exist for new possibilities to emerge, the forgetting that makes new forms of remembering possible. But even if we accept this more optimistic interpretation of unconformities, they still raise profound questions about the nature of time, memory, and the preservation of information in complex systems. They suggest that the universe might be structured in ways that ensure certain types of information are temporary rather than permanent, that some forms of knowledge are meant to be forgotten rather than preserved. This has implications that extend far beyond geology. It suggests that forgetting might be as important as remembering in the evolution of complex systems, that the ability to erase past constraints might be essential for the emergence of new possibilities. Human societies, biological ecosystems, technological systems, all of these might require periodic episodes of creative destruction that erase existing structures and enable the emergence of new forms of organization. The unconformities we see in the geological record might be examples of a more general principle that operates across many different types of complex systems. But this principle operates on such vast scales and long timescales that we can barely perceive it from our limited human perspective. We experience only tiny fragments of these larger cycles of creation and destruction, brief intervals of stability between much larger episodes of transformation. The stable geological conditions that have characterized human history might be just a momentary pause in a much larger cycle of planetary change. a brief interlude between major unconformity events that reshape the entire structure of Earth's surface environment, and the human activities that seem so dramatically important from our perspective. Our alterations to global climate, our modifications of biological ecosystems, our technological innovations might be just minor fluctuations compared to the forces that create and erase geological unconformities. We might be living through a period that future geologists will classify as a minor unconformity, a brief episode of environmental disturbance that temporarily altered surface conditions before being erased by larger-scale processes that operate according to their own vast rhythms. Or we might be living at the beginning of a major unconformity event, the early stages of a planetary transformation that will ultimately erase not just human civilization, but entire geological eras from the rock record. The warming climate, rising sea levels, mass extinctions, and other environmental changes that characterize the current moment might be the first signs of processes that will ultimately operate on scales that dwarf human experience and imagination. But we have no way of knowing which interpretation is correct because unconformity processes operate on timescales that exceed human observation by factors of millions. From our perspective, the Earth seems stable and predictable, with environmental changes occurring gradually over decades or centuries. But from the perspective of geological time, our entire experience might be just a brief moment of apparent stability before the onset of changes that will ultimately prove to be far more dramatic than anything we can currently imagine. The prehistoric time holes that no one can explain might be growing even now, preparing to swallow our era just as completely as they swallowed the billion years that came before us. Every breath you take, every step you make on the Earth's surface is happening during what might be a brief interval of geological calm between episodes of planetary transformation so complete that they erase their own evidence. The rock beneath your feet, the air in your lungs, the water you drink, all of it exists in its current form only because it happened to survive the last major unconformity event and has not yet been consumed by the next one. You are walking on the fragments of deep time, breathing the remnants of ancient atmospheres, surrounded by the survivors of processes that periodically erase entire chapters of planetary history. And somewhere in the depths of geological time, forces that we can barely comprehend are working to prepare the next great erasure, the next prehistoric time hole that will remove all evidence of the current moment and replace it with something entirely new and different. The time hole that no one can explain is not just a feature of Earth's past. It might be the defining characteristic of the planet's future, the mechanism through which the Earth periodically forgets its own history and begins writing new chapters in the story of planetary evolution. In the end, unconformities remind us that impermanence is not just a feature of individual lives or human civilizations, but a fundamental characteristic of planetary existence itself. The Earth does not simply accumulate history, it periodically erases and rewrites its own story, creating gaps in the record that ensure certain episodes remain forever mysterious. The missing time periods represented by unconformities are not just absent from the geological record. They might be necessarily absent, required absences that create the space for new possibilities to emerge. And every moment of your existence occurs within one of these spaces of possibility, surrounded by the evidence of past erasures and the potential for future ones. Part of a planetary story that is always being written and rewritten in ways that ensure it can never be fully told. But let's dig even deeper into what these missing time periods actually contained, because the scale of what's absent from the geological record becomes more staggering the more you understand what should be there. During the billion years represented by the Great Unconformity, the Earth underwent transformations that were arguably more dramatic than anything that has happened since. This wasn't just a quiet period of gradual change that happened to not leave good fossils. This was a time when the fundamental rules of how planets work were being established. The missing time includes the period when plate tectonics first began operating in its modern form. Before this period, the Earth's surface was dominated by different types of geological processes that we can barely reconstruct because the evidence has been erased. Early Earth had a much thinner crust, a different atmospheric composition, and surface temperatures that would have made the planet barely recognizable compared to what we see today. The transition from this alien early Earth to something more recognizable as the modern planet happened during the missing time. We know this transition occurred because we can see its results in the rock layers that were deposited after the Great Unconformity. But we can't observe the transition itself because the rocks that would record it are simply absent. It's like trying to understand how a caterpillar transforms into a butterfly by examining only the caterpillar and the butterfly, with no access to the chrysalis stage where the actual transformation occurs. The missing time also includes the period when the Earth's magnetic field stabilized into something resembling its modern configuration. Before this period, the planet's magnetic field was much weaker and more chaotic, providing little protection from solar radiation and cosmic rays. The development of a stable magnetic field was crucial for the eventual evolution of complex life, but it also involved dramatic changes in the planet's internal structure that would have left clear signatures in the geological record. Yet these signatures are largely absent from the rocks we can study, erased along with everything else during the unconformity events. Even more significantly, the missing time includes the period when the Earth's atmosphere first developed substantial oxygen concentrations through the activity of early photosynthetic organisms. This atmospheric transformation, known as the Great Oxidation Event, was one of the most dramatic environmental changes in Earth's history. It poisoned most of the life forms that had evolved in the oxygen-free environment of early Earth. But it also created the conditions necessary for the evolution of complex multicellular organisms. We can see evidence for this atmospheric transformation in chemical signatures preserved in certain types of rock formations, but most of the direct evidence for how it occurred and what environmental conditions were like during the transition has been removed by unconformities. We're trying to understand one of the most important environmental transitions in Earth's history based on fragments and traces, with the main body of evidence systematically erased. The missing time also encompasses the period when life first began experimenting with multicellularity, sexual reproduction, and other innovations that became the foundation for all subsequent biological evolution. These early experiments in biological complexity were probably much more diverse and strange than anything we see in the modern world. Evolution was exploring possibilities that have no contemporary equivalents, developing forms of biological organization that we can barely imagine. But most of the evidence for these early biological innovations has been erased along with the rock layers that would have preserved them. We catch glimpses of this lost biological diversity in a few exceptional fossil deposits that somehow escaped the erasure processes, but these glimpses only hint at the full scope of what we're missing. It's as if we're trying to understand the history of art by examining only a few random brushstrokes from paintings that have otherwise been completely destroyed. The biological innovations that occurred during the missing time weren't just precursors to modern life forms. They might have included entirely different approaches to biological organization that have no modern equivalents. There might have been forms of multicellular organization that were more sophisticated than anything we see today, biological systems that explored possibilities for complexity and integration that were later abandoned when environmental conditions changed. Some researchers speculate that the early experiments in multicellular life included forms of collective intelligence and distributed processing that wouldn't be out of place in science fiction. But we'll probably never know for certain because the evidence has been systematically removed from the geological record. This pattern of systematic evidence removal extends beyond just the Great Unconformity. Throughout Earth's history, there are smaller but still significant unconformities that have erased evidence of other important transitions and innovations. Each of these missing time periods might contain crucial information about how planetary systems develop and how life responds to environmental change. But the cumulative effect of all these erasures is that our understanding of Earth's history is built on a foundation that is much more fragmentary than most people realize. We're like archaeologists trying to reconstruct an ancient civilization based on scattered pottery shards, with most of the buildings, artwork, and written records having been systematically destroyed by processes we don't understand. The story we tell about Earth's history is necessarily a story constructed from survivors, from the fragments that happen to escape the periodic episodes of geological amnesia that characterize the planet's long-term behavior. But this raises a disturbing question. How much of what we think we know about Earth's history is actually representative of what really happened? If the evidence we have access to represents only the fragments that survived unconformity events, then our understanding of planetary evolution might be systematically biased towards certain types of processes and certain types of outcomes. The most important innovations, the most dramatic transitions, the most significant events in Earth's history might be precisely the events that are least likely to leave traces in the geological record. This could mean that our scientific understanding of how planets work is fundamentally incomplete, based on studying the exceptions rather than the rule. Most of Earth's history might have been characterized by processes and conditions that we can barely imagine because they systematically erase their own evidence. The stable, relatively predictable geological and biological processes that we observe today might be unusual interruptions in a planetary history dominated by much more dynamic and transformative processes. From this perspective, the missing time periods represented by unconformities aren't anomalies in Earth's history. They might be the norm, with the preserved time periods being the real anomalies. We might be living during one of the brief interludes of stability and evidence preservation that punctuate much longer periods of transformation and erasure. But this possibility is almost impossible to test directly because, by definition, we can only study the evidence that has survived, not the evidence that has been systematically removed. It's a classic example of survivor bias on a geological scale. We can only analyze the rock formations that made it through unconformity events, so our understanding of geological processes is necessarily skewed toward the types of formations that are most likely to survive such events. The rock formations that are most vulnerable to unconformity erasure processes might be precisely the formations that would tell us the most about how the Earth really works over deep time. But we'll never be able to study them directly because they've been systematically removed from the record. This creates a fundamental epistemic limitation that goes beyond just missing information. It means that our scientific methods might be inherently incapable of accessing some of the most important aspects of planetary evolution. No matter how sophisticated our analytical techniques become, we can't analyze rocks that don't exist anymore, but there might be indirect ways to study the missing time periods and the processes that erased them. One approach involves looking for what geologists call ghost structures. Subtle traces in surviving rock formations that indicate the former presence of geological features that have since been removed. These ghost structures are like shadows cast by missing mountains, faint impressions left behind by rock formations that were erased so completely that only their indirect effects on surrounding rocks remain. By mapping these ghost structures and analyzing their patterns, geologists might be able to reconstruct at least some information about the missing time periods and the processes that removed them. Another approach involves studying the chemistry of minerals that form during unconformity events. Even if the bulk of the rock record from these periods is missing, there might be chemical signatures preserved in mineral deposits that formed under the extreme conditions associated with unconformity creation. These chemical signatures could provide clues about the environmental conditions that existed during the missing time periods and the processes that were responsible for erasing the geological evidence. A third approach involves looking at the biological innovations that occurred immediately after unconformity events. The forms of life that appeared after major unconformities often show characteristics that suggest they evolved under environmental conditions that no longer exist. By analyzing these post-unconformity life forms and working backwards, biologists might be able to infer something about the environmental conditions that existed during the missing time periods. But all of these indirect approaches provide only fragmentary information about processes and time periods that might hold the keys to understanding how planets really work over geological time. The missing time periods might contain the most important chapters in Earth's history, the episodes when the planet's fundamental characteristics were established and the foundations for all subsequent development were laid. Without access to this information, our understanding of planetary evolution remains necessarily incomplete and potentially misleading. We're trying to understand a story where the most important plot developments have been systematically removed from the narrative. But perhaps this is the point. Perhaps the self-erasing nature of unconformity processes isn't an unfortunate side effect, but an essential feature of how planetary evolution works. Maybe planets need to periodically forget their own past in order to explore new possibilities for development. If geological evidence accumulated indefinitely without ever being erased, the planet might become locked into patterns of development that would prevent it from undergoing the fundamental transitions necessary for long-term evolution. The missing time periods might represent episodes when the normal constraints on geological and biological processes are suspended, allowing for innovations and transformations that wouldn't be possible under normal conditions of evidence accumulation. From this perspective, unconformities aren't just gaps in the geological record. They're necessary gaps that create the space for new types of planetary development to emerge. The erasure of past evidence might be what allows planets to transcend their own history and explore possibilities that would otherwise be blocked by the accumulation of previous constraints. But this interpretation raises its own questions about the nature of planetary evolution and the role of memory and forgetting in complex systems. If forgetting is as important as remembering for the long-term development of planetary systems, then the unconformities we observe in Earth's geological record might be examples of a more general principle that operates across many different types of complex systems. Biological evolution, technological development, social organization, even the evolution of the universe itself might all depend on periodic episodes of creative destruction that erase existing structures and enable the emergence of new possibilities. The missing time periods in Earth's geological record might be windows into understanding how innovation and transformation work on scales that exceed human experience and imagination. But they remain fundamentally mysterious because their most important feature is precisely their absence from the record we can study. The prehistoric time holes that no one can explain might be explained not by what they contain, but by what they make possible through their very emptiness. They might be the spaces of possibility that allow planets to continuously reinvent themselves over billions of years, the necessary absences that enable the presence of new forms of complexity and organization. And if this interpretation is correct, then the time hole that no one can explain isn't just a feature of Earth's past. It's an ongoing process that continues to operate today, creating the conditions for futures that we can't yet imagine because they depend on forgetting constraints that we currently take for granted. The missing time in Earth's geological record might be matched by missing possibilities in our own understanding, gaps in our knowledge that aren't just waiting to be filled, but that need to remain empty in order for new forms of understanding to emerge. Every moment of geological time that you're experiencing right now exists within these larger rhythms of memory and forgetting, preservation, and erasure, the accumulation of evidence and its systematic removal. You are breathing air that has circulated through the missing billion years, walking on ground that bears the invisible traces of erased mountains, existing within a moment that might itself someday become part of the next great unconformity. The time hole that no one can explain surrounds you, encompasses you, makes your existence possible through its very incomprehensibility.